Gray code is non-weighted code. It is developed by Frank Gray, a scientist mathematician. Gray code has many applications in different fields. It has the applications in mathematical puzzles, in genetic algorithms also it has applications. It has applications in electronics also. So this code we are considering from the point of electronics. The code is also known as reflected code or mirror code also. This is because of its construction, mirror code also. We know binary code. In case of binary code, if we consider, then as the numbers decimal go from 0, 1, 2, 3, 4 like that, the binary code is 0, 0, 0, 0 or 4 bit. It can be any number of bits. For gray code also initially it is 0, 0, 0, 0. Binary code flows that 0, 0, 0, 0, then 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, like that it flows. Here, when the state changes from this to this, 1 changes from 0 and 0 changes from 1. Here also when the state changes from this to this, 3 bits, this and this, all the 3 bits change the state. In case of gray code, there is a speciality that in any two consecutive numbers, only 1 bit changes. Only 1 bit changes. So that way it is formed. So next is 0, 0, 0, 1, but now the number becomes a 0, 0, 1, 1. Only this is changed. And the third will, next will be 0, 0, 1, 0. Now when the next bit comes, it becomes 0, 1 and 1, 0. Now you observe here 0, 1 and exactly 1, 0, exactly opposite. So if you put a mirror here, the code is mirrored. The same thing happens for any number of bits. Let's observe this table already prepared. Now see here, this is a gray code and the corresponding binary code. Observe here that this case 0, 0, 0, then 0, 1, 1, 0, 0, 1, 1, 0. It way it is going up. Check the next bit 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0. Next is 4 zeros, 4 ones, then 4 ones, 4 0. In this way it goes on. So there is some equivalence. In case of binary code, if we understand, we know that the weight of this is 0, weight of this is 2 raised to 0, that is 1. This is 2 raised to 1, so 2. This is weight of it's 4 and weight is 4. 8, 4, 2, 1 are the weights. Here gray code is non-weighted code. It does not have any weight. In case of electronics, it has certain applications that it is used in encoder circuits. Encoder circuits. It is used in K-maps. Also, it is sometimes used in ADCs. These are the applications of gray code in electronics. Now, let us understand how to convert gray code to binary and binary to gray. Suppose binary to gray conversion. Now try to remember this figure, this type of figure. For any number of bits the figure continues. So let us consider a binary number B3, B2, B1, B0 is a binary number. Consider any number, suppose 10, 10. Now the procedure is take the first as it is. So this becomes 1. Then do this addition. 1 plus 0. This 1 plus 0. 1 plus 0 is 1. Now do this addition. 0 plus 1. 0 plus 1 is 1. Now do this addition. 1 plus 0 is 1. So 1 0 1 0 becomes 1 1 1 1 as binary to gray. Let's come check it. So 1 0 1 0 you can observe here. This is becoming 1 1 1 1 which is coming here. It is like this. You can observe this. Now from this we understand the procedure. Here the number is G3, G2, G1 and G0. We can have one more number, for example, for 6-bit. Suppose 101101. Then what will be the equivalent number? This is 1. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1. 1 plus 1 is 0. 1 plus 1 sum is 0. 1 plus 0 is 1. 0 plus 1 is 1. This becomes the equivalent number. So, if we want to design the circuit for this, then we can write down the equations for the outputs from the inputs. You can see that G3 is as it is coming from B3. So, we will write that G3 is equal to B3. Now, in this case, we understand that if we do the addition, 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. In all these cases, there is no carry. But when we do 1 plus 1 addition, there is a carry 1 and sum is 0. So we have to consider only sum here. If we write a truth table only for sum, then for A, B and Y, it is 0, 0, 0, 1, 1, 0 and 1, 1. Then for 0, 0 case, the output is 0. For 0, 1, it is 1. For 1, 0, it is again 1. And for 1, 1, it is 0. So this truth table is of XOR gate. This truth table is of XOR gate. So we will use XOR gate in the design of this for the addition. So G3 is equal to B3. Now consider G2. G2 is done by the addition of B3 and B2. So this will be B3 plus B2. G1 is done by addition of B2 and B1. So G1 is equal to B2 plus B1. G0, if you consider, G0 is done by addition of B1 and B0. So this is B1 plus B0. Now we know that B3, B2, B1, B0 are the inputs and G3, G2, G1, G0 are the outputs. So let us draw the circuit for this. It will be a very simple circuit. 4 inputs B3, B2, B1, B0. Let me draw it with some space slightly. B2, B1, B0. Then B3 as it is becoming G3. These are the inputs and these are the outputs. Now G3 is same as B3. G2 is addition. For the addition, we are using XOR gate because the table is XOR gate. So this becomes the equation. So B2 and B3, they are exclusively ORed to generate G2. So G2 will have one input from B3, another from B2. Similarly, G1. G1 will have exclusive OR. The output is G1. One input is B1, another is from B2. Then G0. G0 as one input is B0, another input is from B1. So this forms the circuit of binary to gray conversion for 4-bit. The same circuit will be extended to any number of bits as per requirement. Now let's consider the conversion of gray to binary. As a homework, you can try different numbers, convert them also and check in the table given. In gray to binary, the inputs are gray. So G3, G2, G1, G0 will be the inputs. Let's take any number, suppose 1001 is the input. Convert it to binary. Remember the symbol for this. So this G3 is coming as it is to B3. So it becomes 1. First number, first bit is as it is 1. This is B3. Now this number and this number. So new next number and previous next number. New number and previous next number. They are added to form B2. So 1 plus 0. 1 plus 0 is 1. So B2 is equal to this. Again, this is added to this to find out the answer. So 1 plus 0 is again 1 here. So that becomes, and this 1 plus 1, 1 plus 0 becomes 1 plus 1 is 0. So this becomes B0. So B0, so the answer is 1110 for the input of gray code 1001. Now let's check this. 1001 is now, this is the input. Here this becomes the input, and the corresponding output here, the output is this, is the output 1110. So we have got it correct. Exactly similar calculations we can do for bigger number also. Suppose the number is 5-bit number 10011. Suppose this is the number. Then 1 is coming as it is. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 0. And 0 plus 1 is 1. This becomes the answer of the number of conversion from gray to binary. From the conversion procedure, we have understood that we get now gray codes are the inputs and the binaries are the outputs. So B3 is equal to G3. B2 is addition of, B2 is generated by the addition of B3 and G2. B3 and G2. So B3 XOR G2 because addition is there. B1 is generated by B2 and G1. B2 and G1. So B2 XOR with G1. B0 is generated by B1 and G0. So B1 XOR G0. So let's draw the circuit for this. Now gray codes are on the input side, G3, G2, G1 and G0. Binaries are on the output side, B3, B2, B1 and B0. These are outputs, these are inputs. G3 is going as it is to B3. B2 is generated by XOR gate. B1 is also generated by XOR gate. B0 is also generated by XOR gate. Now what are the inputs? For B2, the inputs are B3 and G2. So G2 is taken and B3 is taken as it is. For B1, the inputs are B2 and G1. So G1 is there and B2 is generated here. So this is taken here and added at the input. B0 is G0 and B1. So G0 is one of the input and B1 is the another input. So this becomes the circuit for conversion of 4-bit gray to binary. This will be extended as it is for any number of bits.